Hi! In Crash Course Physics episode 8, we're going up into space with the help of some centuries-old formula. Newton's derivation of Kepler's 3 laws of planetary motion was a major breakthrough in science and established the field of physics as the truly modern endeavor we know it today. The gravitational force between a planet and the Sun, or any small satellite orbiting a massive body, decreases in strength as the square of the distance. This property of gravity determines the orbit's shape, an ellipse. It's not easy to see why, or at least not simple enough to show in this video. Usual textbook derivations rely on a good deal of calculus, but the inimitable Richard Feynman came up with a purely geometric proof. Kepler's second law states that the connecting line between the Sun and the planet sweeps out equal areas in equal times. This is a weird one. Why would a planet be preoccupied with an imaginary area swept out by an imaginary line? What happens is that this area is a metaphor for the product between the velocity and position vectors. By product, I mean the cross product between vectors, which measures the area of the parallelogram spanned between them. Over a short time interval dt, the triangle swept out by the position vector has sides r and v dt. The rate of change is thus half the parallelogram spanned by r and v. The parallelogram's area never changes. We can understand this by imagining the planet switching between free inertial motion along the direction of v and sudden bursts of gravity from the Sun along the radius. In the first step, the parallelogram is sheared along v, and it is a simple geometric fact that this does not affect the area. In the second step, the shearing occurs along r, and still the area doesn't change. If the orbit is circular, the parallelogram is a rectangle, and its velocity side has the length omega times r, omega being the radial velocity. Thus the area is omega times r squared, which means that the angular velocity is inversely proportional to the radius square. That way, the planet sweeps around the Sun faster the closer it gets, exactly like a coin funnel. The deeper principle behind this is the conservation of angular momentum. The third law is easiest to understand for circular orbits. It links directly to centripetal acceleration, which in this case is caused by gravity. Remember that a equals v squared over r. Another way of expressing this relationship is with the angular velocity omega, which is velocity with the radius divided out. Then a equals omega squared times r. Now, since for gravity this acceleration is inversely proportional to the squared radius, we immediately obtain that the angular velocity square is inversely proportional to the radius cubed. Restated to the period t, which itself is inversely proportional to omega, t squared is proportional to radius cubed. This relationship has an important application for satellites. You see, what if you want a satellite to always face the same spot on the Earth's surface so that you don't have to constantly adjust your satellite dish? For that, the satellite's period has to match that of the Earth's rotation, which is 23 hours, 53 minutes, 4 seconds. Comparing the satellite with the Moon, which is some 384,000 kilometers away, while orbiting us once in 27.3 days, the proportionality between t squared and r cubed gives us an orbital radius for our satellite of 42,300 kilometers, or roughly 7 Earth radiuses. I hope you enjoyed this video. Don't forget to subscribe and follow me on Twitter. See you next time.